Well, good evening, everyone. We're just going to get started here in just a couple minutes, about 6:57 p.m. right now. We'll wait for some people to get in here, and then we'll start shortly. Just a reminder, we'll be on Twitter and Facebook during the entire event. Use hashtag Skywarn. Questions, comments, anything, we'll try to answer that as we go along. It'll be about 2 hours. And we'll have keywords throughout the entire presentation. So hopefully you can get here started right now. You guys can go ahead and share this link with your friends on your social media channels or whatnot. We want to try to get as many people as we can on this, our very first Skywarn, advanced Skywarn training. So we also have a chat room there on the side. You guys feel free to comment in there as well. That's the easiest place. And we'll get started here in about 2 minutes. All right, well, welcome to our Google Hangout for our first ever advanced Skywarn spotter training here at NWS Memphis. My name is Andy Cupey. I am welcome to a meteorologist here at the Weather Service, and I am a member of the AMS and NWA chapter. If you guys do live in the area, you're welcome to join our chapter, and we'll put the link in there later. Anyways, just want to let you guys know, we've got Gary Woodall. He's got over 25 years of experience, spotter training, worked very, very big network when he was out in Dallas-Fort Worth. We're very privileged to have him. So without further ado, I will turn it over to him.
All right, thank you, Andy, and good evening, everybody. Appreciate you all joining us, and thanks also to the Memphis American Meteorological Society National Weather Association chapter for hosting us this evening. This is going to be a pretty fast-paced 2 hours coming up, and hope you find it informative and enjoyable. Now, before we jump into the program itself, just a quick reminder that this is advanced spotter training. We assume coming into this program that you've been through basic spotter training, maybe done some live spotting. We assume that you know what a supercell is, what a wall cloud is, what an updraft is. Our program here this evening is going to kind of pick up where that basic training left off and get more kind of a more scientific discussion into the hows and the whys some of these severe weather events occur and take place. So with that, we will go ahead and jump into the program and be off and on our way. So as Andy mentioned in his introduction, we are going to have several keywords scattered throughout the program. Make sure that you write down those keywords. That's going to be important for you getting your credit for participating in the program this evening. At the end of the session, you'll email the keywords along with some other information that we'll give you later in the program to sr-meg.wx@noaa.gov. Again, that's sr-meg.wx@noaa.gov. And we'll post that information again at the end of the presentation as well. As Andy said, if you have any questions, you can tweet them to us at NWS Memphis. Use the hashtag Skywarns. We'll be able to pick out your questions, or you can post to us on our Facebook page at facebook.com/NWS Memphis. And we also will have that information, the Twitter and the Facebook information, down there at the bottom of all of the slides as well. The outline of what we're going to cover this evening, we'll have a 2-hour program. The first hour, we're going to talk about the ingredients that we need for not just severe thunderstorms, but organized severe storms, because those are the ones that are going to cause the biggest threats to life and property here in the Mid-South. We'll talk about the environments in which these severe storms form, some of the ingredients that have to come together. We'll talk about some of the theories on tornado formation, the mechanisms that have to occur for tornadoes to occur, and talk about some of the ingredients that have to come together, again, not just for supercells, but for potentially tornadic supercells as well. We'll take a 10-minute break about halfway through. When we come back after the break, we'll talk about some real-time analysis tools, things that are out there and available that you can use to keep up with those ingredients and maybe anticipate what types of severe storms we may get on a particular day. We'll talk some about basic radar interpretation, reflectivity, velocity, and a little bit about some of the dual polarization data that we've had for a few years now, and that some of the radar providers are putting on their systems as well. Then we'll kind of tie everything together with a case study, and again, kind of wrap it all up. So what do we need in order to get organized severe thunderstorms? Well, we need the moisture, moisture that's going to go on to form the clouds and the rain and the hail with the storm. We need instability, a warm, moist air down near the ground, relatively cold air, 3-4 miles up in the atmosphere. That, of course, is what makes it favorable for the updrafts and the downdrafts to form in the storm, and we call that thermodynamics. So you can tell right away this is going to be advanced spotter training because we're using much longer words than we do in the basic program. We need to have lift, as with all thunderstorms, something to lift that moist and unstable air and get those updrafts started, get that thunderstorm process actually started and get it moving. We need vertical wind shear, kinematics it's called, in the atmosphere. Now, what do we mean by vertical wind shear? Well, vertical wind shear is defined as a change of wind direction and or speed with height. We can have speed shear, in which the direction stays the same, but the wind speeds change. And usually in the atmosphere, it's the wind speeds increasing as we go up with height. As we see here, again, the wind's getting faster as we go higher up in the atmosphere. Or we can have directional shear, where the speed stays the same and the direction changes. And that's what we're showing here, with, again, the speed staying the same, but in this case, going from a southeast to a south to a southwest to a west wind as we go up through the atmosphere. Now, usually we have both speed shear and directional shear taking place in the atmosphere on a typical severe weather day. Whoops. So, atmospheric stability or instability. The easiest way to think about this is to think about a parcel of air, a blob of air, maybe about the size of the room that you're in. Now, if we can lift that parcel, if we can get that parcel to start rising, and if that parcel of air, that blob of air, becomes warmer than the surrounding air, it's less dense, it's going to continue to rise on its own. That's what produces the updrafts and the thunderstorms. When we have that, we say that the atmosphere is unstable. Now, on the other hand, if we lift that parcel of air and it becomes cooler than the environment, it's going to be heavier, more dense than the environment, and that parcel, that blob of air, is going to sink back down to where it started. An easy way to think about this: warm air likes to rise, cold air likes to sink. When we measure instability in the atmosphere, we use a unit called CAPE, which stands for Convective Available Potential Energy. Again, that's the energy. How much energy is in the atmosphere that can be released when thunderstorms form? And while it's not important to you all, we do measure CAPE in units of joules per kilogram of air. We also measure a quantity called SIN, which stands for Convective Inhibition. That is basically the cap. That is, oftentimes there will be a stable layer, maybe 1.5 miles, 2 miles or so up in the atmosphere, and that can block developing updrafts. It literally acts like a lid on the lower portion of the atmosphere. Having a little bit of a lid is actually beneficial for severe thunderstorms to form, but if the lid is too strong, then none of those developing updrafts can break through, and we may not get any thunderstorms at all. So again, CAPE and SIN, again, basically energy measurements, and both are measured in joules per kilogram of air. So let's talk a little bit more about instability. Again, this CAPE, Convective Available Potential Energy, is the measure of how much buoyant energy do we have through the depth of the atmosphere, through the potential depth that thunderstorm may develop in. Convective inhibition, again, the stable layer, the cap strength through which we've got to lift our blobs of air, our parcels of air, to get those updrafts to form. And again, both measured in joules per kilogram of air. So visually, as a storm spotter, there are some important things you can look for that might suggest areas of SIN, areas of CAPE, and some other important layers in the atmosphere as well. One very important level or layer that we're going to talk about a little later on this evening is called the lifted condensation level, LCL. That's just a big fancy term for the cloud base. And the height of the cloud base can be very important when it comes to the tornado process. SIN, again, will be that stable layer, that lid through which our parcels, our blobs of air have to be lifted or forced up through in order to go on and develop substantial updrafts and to get the thunderstorm process going. Now, typically, visually, if we have SIN in the atmosphere, the clouds in that stable layer will oftentimes be very smooth looking, laminar it's called, very smooth looking, not a lot of the bubbly, boiling look, the cauliflower look like we see with the active updrafts area. The LFC, or level of free convection, that's the level that we need to lift our blobs, our parcels of air to, for them to become warmer than the environment, for them to take off on their own and go on and form updrafts and start the thunderstorm process. And then again, CAPE, this area in which the updrafts are rapidly growing and developing upward. Now, we have different types of CAPE that we can measure and evaluate as well. And to do that, we take a blob of air somewhere here in the lower part of the atmosphere, lift that blob of air, and compare it to the environment. Again, seeing if it's warmer or cooler than the environment, and using that to calculate how much energy is available for the thunderstorms. We can take a blob of air from right off of the surface, right off of the ground, and lift it. When we do that, it's called surface-based CAPE, or it's abbreviated SB CAPE. You may see that abbreviation. If you read the Storm Prediction Center outlooks and discussions, you may see them refer to SB CAPE from time to time. Again, that's surface-based CAPE, lifting the parcel from right off the ground. A lot of times, though, we will use what's called mixed layer CAPE. For mixed layer CAPE, we calculate an average temperature and dew point, humidity, average conditions in the lowest about mile or so of the atmosphere, and we lift that average parcel, that average blob of air. Now, ML CAPE will typically not give us values that are as high as the surface base, the SB CAPE, but usually this is a better representation of the actual conditions in the atmosphere in, say, the mid to late afternoon or early evening hours, when we tend to have a lot of our severe thunderstorms forming. In the atmosphere, it's kind of mixed up, it's kind of churned up a little bit in the lower levels, so maybe a little more accurate measurement of the energy that's there. There's also a flavor of CAPE that's called most unstable CAPE, or MU CAPE, and this takes a little bit more calculation. For Mu Cape, we look through the lowest about 2 miles or so of the atmosphere and find the most unstable layer anywhere in there. And then that's the layer that we will actually lift. Those are the blobs of air that we'll actually lift to do the energy calculation. Now, why would we want to do this? It seems like an awful lot of extra work. Well, sometimes if we have a shallow cold front moving through the area, we can sometimes get thunderstorms. The lift for those thunderstorms occurs up above that cold front. And so we can get thunderstorms forming above a layer of cold air that's down near the ground. So Mu Cape, the most unstable cape, can help us see those situations if we have the potential for thunderstorms after a cold front has moved through, for example. Okay, so that's the instability, again, some of the thermodynamics that we look at. Now let's take a look at vertical wind shear, a little closer look at it. Vertical wind shear is absolutely crucial when it comes to organized, long-lived thunderstorms. And again, those are the storms that are going to be potentially the biggest severe weather producers. Again, vertical wind shear, a change of wind direction and or wind speed with height. And again, we usually have both directional shear and speed shear going on in the atmosphere on a particular severe weather day. Now, a quantity or a term that you'll hear sometimes is bulk shear. And what exactly does that mean? Well, that is the net change, the net amount of wind shear that we see through a particular layer of the atmosphere. It's also sometimes called the bulk wind difference. But when we're talking about wind shear, usually it is this bulk shear that we're talking about. And here's a little example to hopefully make it a little clearer for you. Here we have a wind, say at the lower portion of our layer, that's coming from the southeast in this direction. At the top of our layer, the green arrow shows the winds there, and we have winds from the southwest as we show here. So the net difference between this wind and this wind is shown by this red arrow. So that would be the bulk shear throughout this layer. And we can measure the length of this red arrow, equate it to a speed, an amount of knots basically of change of wind speed and or direction. And this is how we quantify this vertical wind shear, how we measure the vertical wind shear and determine if we have enough vertical wind shear for these organized thunderstorms to form. We'll get into all that in a lot more detail as we go on through the rest of this first hour. Now, we talked about shear being through the vertical wind shear being through a depth of the atmosphere. There are some important shear layers that we look at. 0 to 6 kilometers or 0 to about 4 miles or so up above the ground. That is sort of our standard layer or standard level for what we call deep layer vertical wind shear. Deep layer vertical shear is important because it can help ventilate the storm, allowing the storm to last for a longer period of time. And that deep layer shear can help with forming mid-level rotation, a mid-level mesocyclone within the thunderstorm. There's also a layer that's called effective vertical wind shear. And the effective layer is essentially 1/2 of what the estimated storm height would be on a particular day. Again, probably seems like a little bit extra work that we're having to do there. Why not just use 0 to 6 kilometers all the time? Well, sometimes, and depending on the environment, we can have particularly short storms or particularly tall storms. During the wintertime or the very early spring, our storms, while they can be very severe, may not be all that tall. So 0 to 6 kilometer may be sampling too deep a layer in the storm. On the other hand, as we get into late May and early June, our storms can be very tall. In those cases, excuse me, the 0 to 6 kilometer may be a little bit too short. So effective vertical wind shear is a better measure. It accounts for those particularly short or particularly tall storms. Another important layer, 0 to 1 kilometer, so about the lowest 2/3 of a mile in the atmosphere. This is an important parameter for getting low-level rotation, getting a low-level mesocyclone established down towards the base of the storm. So here's an example of a thunderstorm that's formed in an environment with a weak deep layer vertical wind shear. Very little change of wind direction and wind speed as we go through the height of the atmosphere, through the height of the storm. And what we see is that the updraft basically goes straight up. We produce the precipitation, we produce the downdraft, and the precipitation of the downdraft falls basically straight back down through the updraft of the storm. That is going to choke off the updraft of the storm pretty quickly, and we wind up with storms that don't last for a long time, maybe 25 to 30 minutes or so on the average. Also down here at the ground, the gust front, the outflow will very quickly push out away from the storm. That's going to cut off the inflow, cut off the fuel supply for the storm, and again lead to these weak deep layer shear storms, this weak deep layer shear environment, favoring these fairly short-lived thunderstorms. Now, by contrast, this is a computer simulation that I'm going to show here in just a moment of a storm that formed in an environment with strong deep layer shear. You'll be able to watch these little ping pong balls here and some arrows that will get ingested into the simulated storm and see what happens to them. So here's the updraft going up, again picking up these arrows and these ping pong balls. Notice here that everything is basically being blown downwind, downstream, away from the updraft area. So we're ventilating the updraft. We've opened up the flue of the fireplace chimney here and again ventilating the upper portion of the storm. This will also help separate the updraft area from the downdraft. The updraft goes up here, the rain and the downdraft falling out in this area here. So nothing really gets in the way of the updraft, nothing really gets in the way of the downdraft, and we wind up with storms that last for quite a bit longer. Also, again, this deep layer shear can help induce mid-level rotation, the mid-level mesocyclone within the storm. We'll talk about that process here in just a little bit as well. So if shear is good and more shear is better, can we ever reach a point where we have too much vertical wind shear? And the answer there is yes, we can. So let's look at the combination of instability and vertical wind shear. We'll have instability here going up on the left, vertical wind shear going up as we go to the right in this diagram. So if we have low instability, low amounts of instability, we'll tend to have an environment that favors weak updrafts and weak downdrafts in the storm. As the instability increases, the environment becomes more favorable for strong updrafts and strong downdrafts to occur. Taking a look at the vertical wind shear now, if we have weak vertical wind shear, that tends to support short-lived updrafts and downdrafts. As the vertical wind shear increases, we tend to get environments that are more favorable for long-lived updrafts and downdrafts. Now, we can reach a point if we have weak instability and extremely strong vertical wind shear. The environment's just not favorable for thunderstorms at all. The strong vertical wind shear literally tears those weak updrafts apart as they try to form. But the most volatile combination, strong instability, strong vertical wind shear, is when that's the environment that's most favorable for our most significant severe thunderstorms. Now, thunderstorms can be divided into a spectrum. We touched on a couple members of the spectrum in the Basic Spotter program, but essentially we can have ordinary cells, the garden variety, non-severe type thunderstorms. We can have multicells, and those can consist of small clusters of thunderstorms, of cells, or the larger multicells, the squall lines, the bow echoes, something called a derecho that we'll talk about here in just a little bit. And then we have the supercells and the various variations that we can find with supercells. And while we have variations here, again, the thing which separates the supercells from the other storm types is the mesocyclone, the storm scale rotation that's taking place. So focusing on these, first off with these large multi-cell storms, squall lines, the common name. You also may see or hear the abbreviation QLCS, which stands for Quasi-Linear Convective System. Quite a mouthful there, but basically that's just another name for a large squall line. With these large multi-cells, these QLCSs, we tend to have a number of cells, number of individual updrafts and downdrafts that are all pretty much in the same stage of their life cycle. We tend to get the squall lines when we have a lot of lift, a lot of very, very strong small scale lift, as we see along a cold front that's advancing through the area, or if these storms have produced a large gust front where all the outflows have kind of congealed together into one big large gust front outflow that's rushing out away from the storms. That can provide a lot of lift along this leading edge and keep this line type appearance that we see with these QLCSs, these very large scale multi-cell storms. Now, as these develop and mature, we can get some really complex airflow and circulation and precipitation that occurs in these large scale squall lines. We'll touch on that here in just a moment. Now, if the line is more than about 60 miles, 100 kilometers in length, it might be called a mesoscale convective system, or an MCS. Again, just another term for a very large scale multi-cell type storm or a QLCS type of storm. These large multi-cell storms tend to form in environments with moderate to possibly strong instability, moderate to possibly strong vertical wind shear as well. We tend to have, with these long-lived lines, a very good balance between the motion of the cells, the individual storms in the line, and the motion of the gust front, the outflow, also sometimes called the cold pool, moving along as well. So we don't have one outrunning the other. The outflow doesn't outrun the storm, so it cuts off the inflow. The storms don't outrun the outflow, so they don't lose their source of lift there at the leading edge. So good balance of motion between the cells and the outflow. The vertical wind shear may induce some circulations in some of the cells that can enhance the severe weather potential in those cells, as you would probably expect. We also can get low-level circulations that develop with these lines, these QLCSs, especially the fast-moving lines that we often see during the winter and the early spring months. And with these QLCSs, these big lines of thunderstorms, because of these low-level circulations, because of the airflow that we see, the overall airflow and the overall structure, these can be our big-time damaging wind-producing storms when they come through. So this kind of busy, kind of complicated looking diagram is what a side view of one of these large squall lines, one of these large multi-cell storms might look like, moving from left to right across the screen. So here at the leading edge of the storm, again, moving from left to right across the screen. So here at the leading edge of the storm, we have the new updrafts that are being lifted by the gust front, by the outflow pushing out away from the storm. Mature cells in this area here, that's where the heaviest rain, possibly the hail, might be found. Of course, up at the top of the storm, we have the updrafts slowing down and spreading out, forming the anvil, the big flat top formation up at the top of the storm. But we also will have some of the airflow that comes in through the updraft, actually kind of through the downdraft a little bit, and then back towards the rear portion of the storm. Now, underneath this area, we have something important that takes place, this descending rear inflow area. This air will come into the back of the storm, the back of the line from the rear, and will eventually be brought down to the ground, maybe in the heavy rain area, maybe just a little bit one side or the other. And this is what helps produce, again, that large gust front, that large area of outflow at the leading edge here. But if these rear inflow winds get very strong, as they come down to the ground, they can slam into the ground very quickly, move out in this area, accelerate this portion of the line in this area where we're getting those very strong rear inflow winds, and that can then produce the bow echo, which we talked about some in the basic program. Again, strong rear inflow coming into the back portion of the storm, the line in this area here, coming to the ground, accelerating this portion out ahead and producing this bow type shape that we see on radar. And again, this leading edge here, where these strong winds are coming down to the ground and starting to surge out, that's going to be our leading area, our primary area of damaging wind threat. To the north of the leading edge of the bow, the apex of the bow, sometimes short-lived tornadoes can occur. And these bow echoes, sometimes they're fairly short-lived, may last for only 30, 45 minutes, an hour or so. Other cases, again, with very large storms, very well-organized storms, they can persist for many hours as well. When they do that, they can evolve into what's called a derecho, a long-lived, widespread, damaging wind-producing storm. Some derechos have gone on for almost 24 hours, going across a good portion of the country. We've seen some that start up in the Midwest, Illinois, Indiana, move all the way over to near the East Coast of the U.S. The Memorial Day weekend storm last year was an example of a derecho as well. It just barely met the distance requirement to be considered a derecho. But again, widespread wind-producing storms that move through, damaging wind-producing storms that move through. Now again, sometimes along these fast-moving lines of thunderstorms, we can get these little surface-based or near-surface-based circulations that will occur, and these are called mesovortices. Again, they form at the leading edge, typically with, again, fast-moving lines of thunderstorms. These mesovortices can be in some cases, favored areas for tornado production. We've seen many occasions the last few years of mesovortices that have produced tornadoes here in the Mid-South. But even if we don't have tornadoes from these mesovortices, they can be associated with an enhanced damaging wind potential as well. We can still get swaths of enhanced wind damage as these mesovortices move across. Now, they typically, while they are rotations that are associated with the thunderstorm, they usually don't last long enough and don't go through a big enough depth of the storm to actually be classified as mesocyclones, like we talk about with supercells. But again, they can produce tornadoes. They can be areas where enhanced wind damage may be taking place. So now let's talk about supercells a little bit. And again, the main thing which separates the supercell from the other storm types is the rotation, the mesocyclone, the large-scale, updraft tower scale storm rotation that's taking place. Of course, here we have the classic supercell with the heavy rain area off here to the far right, looking at this storm off to the west or northwest, as you probably would guess. The large hail in this area here, again, just to the north or northeast of the updraft area. The updraft tower, again, marking that main updraft area of the storm. The rain-free base underneath, the low-level feature marking that general updraft area. And the wall cloud marking that area of strongest updraft in the storm. Now, with classic supercells, of course, with the supercells in general, again, some of the ways to identify that mesocyclone, the round look, the cylinder look to the updraft tower, the striations, those streaks or bands on the side of the updraft tower that might give the storm kind of a corkscrew or kind of a barber pole appearance. The inflow bands, the tail cloud as we show here, or the beaver tail, which may be coming into the rain-free base area. Again, all visual clues which might suggest that you're watching a supercell, a storm that has, again, this large-scale, updraft tower scale rotation that's taking place. So we talked in the basic program about classic supercells and about high precipitation or HP supercells. What are some of the things that we see in the environment that can make the environment favorable for one type of supercell or the other? Well, a lot of it has to do with how strong the winds are up here at the upper levels of the storm, up towards the top of the storm where the anvil has formed. With a classic supercell, we tend to have fairly strong winds up here at anvil level, blowing across. And so what's going to happen then is those strong winds will blow all that rain and hail out downwind, downstream, away from the updraft, away from the mesocyclone. High precipitation supercells, though, again, will tend to have more rain and hail wrapping around the west or the southwest side of the storm. In some cases, that rain and hail may completely wrap around or almost completely wrap around the rain-free base area, obscuring some of those important parts of the storm, making it difficult to see, as a storm spotter, some of these important low-level clues that we're going to want to look for. Now, with a high precipitation supercell, we tend to find these winds up at the top of the storm just a little bit weaker, strong enough still for the storm to be able to rotate, but not as strong as with the classic supercell. So what happens, instead of the rain and hail falling out in this area here, downwind of the updraft area, some of that rain and hail gets caught up in the mesocyclone, wraps back around, and falls out in this area here, and again leads to a lot more rain and hail falling out of this portion of the storm. Now, in some cases, there have been some observations of storms with extremely strong mesocyclones. Even if the anvil level winds are strong enough, this mesocyclone can be just so big and so strong that it literally grabs some of this rain and hail over here and yanks it around the western and southwestern and southern sides of the mesocyclone. But usually, again, it's the anvil level winds, the winds up at the top of the storm. For classic supercells, a little stronger winds. For HPs, a little bit weaker winds, so more of the precipitation gets caught up in the mesocyclone. That brings us to our first keyword of the evening. Again, if you want training credit, be sure and copy these keywords down and email them to us with the instructions we'll give you at the end of the program. So our first keyword is shear. Shear. So go ahead and copy that down. Now, in order to get a tornado, oftentimes a three-step process will occur within the storm and the storm's environment. The first stage of the process is getting a mid-level mesocyclone, mid-level rotation established in the storm. And again, the mid-level rotation is formed by the deep layer shear. The deep layer shear can actually generate what's called horizontal vorticity, a horizontal rolling motion in the atmosphere, maybe 2 or 3 miles or so in diameter. Again, just kind of this rolling motion that takes place. We'll show some graphs and some animations to show how this happens here in just a little bit. The updraft, as the storm forms, the updraft will take that horizontal rolling motion and tilt it up into the vertical. Kind of like if you're out in your driveway or in your front yard, you reach down to pick up the garden hose. The garden hose kind of forms a hump there in the middle where you pick it up, but the garden hose tilts up into the vertical on either side of where you've grabbed it. Well, the updraft can do a similar thing to that horizontal vorticity in the atmosphere. The maximum tilting occurs where the strongest updrafts occurs, and the strongest updrafts are usually in the mid-levels of the storm, so that's where the mid-level rotation will tend to form. The rotation will tend to form in the mid-levels of the storm. Now, the vertical wind profile can also affect how that mid-level rotation evolves once it gets started. We'll talk about that here in just a few minutes as well. Now, once the rotation, the mid-level rotation gets established, that can help cause acceleration of the updraft. It's actually a little low pressure area up there in the mid-level of the storm. So the updraft air is going to rush up towards that low pressure area, and the updraft can be accelerated, stronger than just what the instability might suggest from the storm. Of course, the stronger the updraft, the larger the hail that storm might be able to produce. Also, the rotation can kind of stabilize and balance the updraft and also help the storm, the supercell, to last for a longer period of time. Now, in order to evaluate the vertical wind shear, both deep layer and low-level shear to a degree, we use something called a hodograph. And what the heck is this that we're looking at? Well, the hodograph is basically a plot of the winds from the environment, either from a balloon that's been released, a weather balloon that's measured the winds in the mid and upper atmosphere, or what we might get from an aircraft that's taking off or landing in the area, or what we might be able to get to forecast winds from our computer models. But we basically take these winds and plot them on what's called a polar coordinate system. So this low-level wind, that represents a south-southwest wind at about 10 miles an hour. Southwest winds here, those are plotted up in here. West winds up higher up, those are the little points that you see here. And then we connect all of those points with a line, the red line that you see here. That red line is what we call the hodograph. And the size and the shape of that hodograph will give us a good idea, good feel of what the vertical wind shear is like if we have directional shear, if we have speed shear, what type of environment, what type of wind shear environment is that storm going to have. So if we go through this exercise, and we have computer programs that will help us with this, and there are websites online that will show and display hodographs as well. But if we construct our hodograph for a particular day and draw that red line connecting all those points of the winds, and we get a hodograph that is just about a straight line, like we see here, that is going to suggest multicells, squall lines might be favored. If we have enough deep layer shear, if there's enough of a change from the ground up to that 6 kilometer layer or that effective deep layer shear layer, if we have enough vertical wind shear in there, we may actually get splitting thunderstorms that will occur. The storm will actually split into two, kind of like a human's or a biological cell dividing into two. And if we have splitting storms, the left mover will actually rotate backward anticyclonically or clockwise. The right mover will rotate counterclockwise or cyclonically. So here's a little animation that shows that. We'll put this in motion here in just a minute. We're looking off to the northwest, and here is the winds in the atmosphere on that particular day. Winds from east to west, down low. Winds from west to east, up above. So this would be basically a straight hodograph, but we do have a lot of vertical wind shear. So you can imagine if we put a paddle wheel right about in this area here, well, these winds are going to blow that way, these winds are going to blow this way, and that's going to cause our paddle wheel in here to start to turn. That actually goes on in the atmosphere, and this is what produces that horizontal vorticity, that horizontal rolling motion, large-scale rolling motion that takes place in the atmosphere. Now, the axis around which this horizontal rolling is taking place, this horizontal vorticity is taking place, this axis is called a vortex line. And you'll hear us talk about vortex lines some here when we talk about low-level mesocyclones and when we talk about tornadoes as well. So let me put this into motion for you. Again, looking off to the northwest, we have winds from the east down low, winds from the west up above. We get our horizontal rolling motion, the vortex line, the axis around which that rolling is taking place. So here comes the storm's updraft. And again, as it goes up, just like you picking up your garden hose out of your front yard, it tilts that vortex line up, kind of makes it into a hump type shape. Cyclonic rotation on the south side, anticyclonic rotation on the north side. And we'll let it loop through once more for you. Again, the updraft tilts that horizontal vorticity up into the vertical in the mid-levels, and we get the mid-level mesocyclone, cyclonic on the south side, anticyclonic on the north side. So, okay, we have mid-level rotation in the thunderstorm now. But notice that the rotation and the updraft are not aligned with each other. The rotation is here or here. The updraft is here in the middle. So we still need to do some work in this case for the updraft and the rotation to get combined, to join forces, to join together with one another. And here's an example that shows what happens when we have one of these straight hodographs. This is going to be a computer simulation, another computer simulation. looking in the mid-levels of the thunderstorm. Now, as we start the animation, you'll see some colored shades appear. That's the simulated radar, what we'd see at that point. You'll see some yellow lines that will show up. Those will be where the updraft is taking place. The more lines you see together, the stronger the updraft. And then you'll see these arrows, which are the horizontal winds, the environmental winds, changing as well. So we'll put this into motion. And there's our storm forming, the updraft going up, our first precipitation forming. There, the storm has split, almost like a cell dividing. We have the right mover rotating cyclonically, the left mover rotating anticyclonically. Notice the storms have just about become mirror images of one another. And eventually we do have, again, cyclonic and anticyclonically rotating supercells, but it took a long time to do that. It took the storm split and the new updrafts forming on the south and the north flanks of the storms, of the splits, in order to get the updraft and the rotation combined into the same location with each other. Again, it took a long time. This is a screen capture at 40 minutes into the simulation. Just starting to get a little bit of rotation, the updraft here in the middle. An hour and 10 minutes in, we're finally getting, again, those updrafts and the rotation correlated with each other, taking place at the same time in the same place. So straight hodographs, again, multicell storms, lines, maybe these splitting storms that may get mid-level mesocyclones at least, but it's going to take a while for that to happen. So what happens if we have a curved hodograph like we show here? Clockwise curvature in the lower portion of the hodograph. So clockwise turning of the winds in the lower mile or two of the storm. Well, that produces what's called veering. That's the term for this clockwise turning of the winds, directional shear in the lower levels of the atmosphere. Now, in this case, we may get a storm split still, but the cyclonically rotating storm is going to be favored, much favored, in fact. We have another quantity that we calculate called storm relative helicity. That's basically a calculation of how strong are the winds and how much veering of the winds, the storm relative winds, are in the lower portion of the atmosphere. That can tell us how conducive the storm is not only to rotating, but maybe down the line getting low-level rotation established in the storm as well. Now, one important thing about storm relative helicity, we've got to know or have to estimate the storm motion to be able to calculate what the storm relative winds are. So we have to make a little bit of an estimate, a little bit of a guess to try to calculate storm relative helicity. So when we get a curved hodograph, I don't have an animation for this, unfortunately, but we do have a picture of what it would look like. Again, here's the environment in which the storm is formed. We have east winds turning to southeast, to south, to southwest, to west. So we have directional shear that is present in this environment. Well, now when the storm forms, we have the updraft and the storm rotation kind of coming together very quickly, becoming combined, collaborating with each other much quicker and much easier than we have with the straight hodograph environment. And an example here, again, the same type computer simulation as we saw a few minutes ago, but this time looking at the curved hodograph. We'll put this into motion. The storm forms. It very quickly evolves into a cyclonically rotating supercell. We get a little split, but not a lot of structure with our northern storm. Very strong updraft, very strong cyclonic rotation with our southern storm. In fact, one more split up here, and the right mover from that split starts to rotate cyclonically as well. So again, a much easier, much faster process to get the updraft and the storm rotation combined together in this curved hodograph case. There we are, just 30 minutes into the rotation, already have the updraft and the rotation combined or collaborating with each other. And 55 minutes, very strong updraft, very strong cyclonic rotation. So again, the curved hodograph, the directional shear seems to be really important for getting the cyclonically rotating supercell. And you'll see that discussed a lot in the Storm Prediction Center's outlooks and some of their discussions. They'll talk about large curved hodographs and favoring supercells, or maybe favoring strong mesocyclones. And that's why, because again, the environment is much more favorable for these cyclonically rotating storms to form and prosper. So, okay, we've got our mid-level mesocyclone. The next step is to get low-level rotation developed. And a lot of these processes are kind of similar to what we talked about earlier, but just focused down in the lowest half mile or so, 2/3 of a mile of the atmosphere. We look at the 0 to 1 kilometer storm relative helicity, again, focusing down low in the storm. 0 to 1 kilometer vertical wind shear. These can be somewhat related to each other. The advantage of the vertical wind shear, we don't need to know the storm motion to be able to calculate it. We just look at the wind at the surface, the wind 0.6 of a mile, 1 kilometer up, and get the difference. Low-level boundaries, if there's a warm front or an old outflow boundary that's laying across the area, that can help with low-level rotation. Low-level instability is going to be important as well. Having that instability down very low in the atmosphere so the updrafts can really accelerate once they get started up into the storm. So these environments, again, the vertical wind shear, directional shear in that lower level of the atmosphere will generate that horizontal vorticity, that rolling motion like we talked about earlier, but it's focused down very low into the storm. The updraft will grab that vorticity, those vortex lines, tilt it up into the vertical, and then accelerating the updraft. That's why we need that instability down low, so we can accelerate the updraft very quickly. That's going to stretch that vorticity and help enhance that low-level rotation within the storm. Now, this stretching, a good way to think of that, if you can imagine taking a bungee cord and holding each end of the bungee cord, spinning it around, and it'll spin at a certain rate. Well, if you stretch that bungee cord tight, it's going to spin faster. Well, the same thing happens with the rotation, the vorticity in the atmosphere. If we can stretch it somehow, it's going to intensify that rotation. Boundaries can be very important as well. So here we have a storm. We're going to start out, this is the storm at one time, a later time, and then an even later time up here to the northeast. So early on, this first stage here, we have our storm. We have deep layer shear. So we've established the mid-level mesocyclone in the storm. So it is a supercell. And we have a boundary, an old outflow boundary, or maybe a little warm front laying across this area here. Very warm and moist down here on the south side of the boundary. So we've got good fuel flowing into the storm. That updraft's just going to keep on going. Our surface winds on the south side of the boundary are shown by the yellow arrows coming up from the south-southeast. And our winds 1 kilometer, again, about 0.6 of a mile up above the ground, shown by the green arrows. So if we look in this area here, that would be our 0 to 1 kilometer vertical wind shear on the south side of the boundary. So our storm chugs along and it goes across the boundary. Now on the north side of the boundary, our winds are from the east, or maybe from the east-northeast, like we show with the blue arrows. So now if we look at the 0 to 1 kilometer vertical wind shear on the north side of the boundary, look at how much stronger the 0 to 1 kilometer shear is on the north side of the boundary compared to the south side. So a much more favorable environment as far as the winds are concerned to get that horizontal vorticity really spinning just on the south side of the boundary. The boundary itself can have a lot of vortex lines in here as well. A lot of turning and rolling can occur. That horizontal rolling can occur along the boundary as well. So a lot of vortex lines here, much stronger 0 to 1 kilometer vertical wind shear. So if the air on the north side of this boundary is still fairly warm and still fairly moist and unstable, as this storm crosses the boundary, it's going to ingest all these favorable ingredients, and that updraft is going to pick up all this horizontal vorticity, tilt it, stretch it, and get the low-level mesocyclone established within the storm. So whenever we see storms that are riding along an old weak boundary or crossing an old weak boundary like this, a weak boundary, and we know that it's still fairly unstable on the north side of the boundary, we get really concerned because that storm could be getting into a very favorable environment for low-level rotation. We saw that a lot actually with the storms up in northeast Arkansas and northwest Tennessee, February 24th of this year. There was a little warm front up there, and as the storms that were near the warm front were the ones that produced all the tornadoes that occurred. Now, eventually, as the storm moves away from this most favored area, it's going to get into areas where there's less instability, cooler, not as moist air up in here. So at that point, the storm is going to kind of weaken and start to lose some of its structure. Okay, so the last part of the tornado process is actually getting the rotation down to the ground. So far in the first two stages, we've talked about the updraft, pulling things up into the storm. Well, now we need to talk about getting rotation down to the ground. Now, as we touched on in the basic spotter program, the rear flank downdraft seems to be an important player as far as this is concerned. As the rear flank downdraft comes down, we have the strongest downward motion here in the middle of the RFD, weaker downward motion out here on the edges. So that's going to tend to produce sort of a rolling effect on the edge of the rear flank downdraft, kind of like smoke rings almost, but going down instead of going up. And so in these smoke rings, if you will, again, these edges or areas of the rolling motion on the edge of the RFD, again, the rolling will be in this general direction, like I'm showing. Hopefully that shows up okay on the Hangouts, but the rotation will be in this general direction. So the rear flank downdraft brings these all the way down to the ground. They then will rotate a little bit due to the mesocyclone underneath the updraft area. And now we do get the updraft doing work again, picking up these vortex lines, sort of making an arch out of them. Again, cyclonic rotation on the north side of the RFD, anticyclonic rotation on the south side. Because this is happening basically right off the ground, this is the vortex line, or these are the vortex lines that, as they get stretched by the strong updraft area, produce the tornado. That's one of the theories anyway that's out there, kind of an exotic theory, I know, but that's one of the theories as to how the rear flank downdraft helps get tornadoes going. Now here's that theory kind of superimposed on a real live thunderstorm to hopefully help visualize it a little bit more. Don't worry about this vortex line and this tilting out here. That's the deep layer shear like we talked about earlier. We have the rear flank downdraft in this area here. You can see the clear slot forming back in there. Here's our rain-free base. There's the wall clouds. So that's where the strongest updraft is taking place. So the rear flank downdraft comes down. Again, we're getting the rolling on the edges of the rear flank downdraft. It comes down, hits the ground, gets pushed under the main updraft area, arched up like we see here. Look at there, this part right associated with the wall cloud, the strongest updraft, as we talked about in the basic program, the basic spotter program. So that would be where the tornado forms. Now, what about this anticyclonic part out over here on the south flank of the storm? Well, a lot of times this will just kind of drift off and not really do much of anything. But in some cases, we can have a very large, very strong updraft area up in here. If we have a strong enough updraft here on the south flank of the storm, it may pick up this portion of the vortex line, stretch it up, and form an anticyclonic tornado on the south flank of the mesocyclone, with again the main cyclonic rotation up here to the north. So that's it, kind of again superimposed on a real live thunderstorm to help visualize it. Another theory that again centers on the rear flank downdraft focuses on horizontal shear. So again, there's the storm, there's the hook echo, the mesocyclone right about in this area here, right about on Montrose here. The rear flank downdraft will be coming down and wrapping around in this area here. So the rear flank downdraft is coming out to the east, as we show with the red arrows. The strong inflow coming into the updraft area, as we've shown by the white arrow. So right in this region here, we may have an area of enhanced cyclonic shear, cyclonic vertically oriented twisting that's occurring in this area here. Again, that will also be right where the strongest updraft is, so that could also perhaps be picked up, stretched by the updraft, and help concentrate the rotation, the vorticity here into a tornado. And then again, on the south flank, we may have anticyclonic shear. So that's a couple of the theories that are out there. Again, focusing on the rear flank downdraft and how tornadoes may wind up forming. Is there any radar evidence that might suggest this? Well, yeah, there kind of is. This is from a high resolution research radar, the Doppler on wheels. This is from the Vortex project many years ago. This is the reflectivity right in here. So there's the main rain and hail area with the storm. There's the hook echo. But look at this little anticyclonic, this little backward hook echo sticking off in this area here. So cyclonic to the north, anticyclonic to the south. Many years later, looking from one of the Weather Service, WSR 88Ds, one of our weather radars. Again, there's the main rain and hail area, cyclonic hook echo here, and a little one of these anticyclonic things off to the south. So there is some radar evidence that suggests that some combination of these theories could actually be taking place. Is there any visual evidence? Well, yes, there is. I'll put this into motion. Looking off to the north here, there's the cyclonic rotation in the background. There's the clear slot from the rear flank downdraft. Anticyclonic rotation here in the foreground. Looking to the north, tornado, cyclonic rotation to the north. There's the clear slot from the rear flank downdraft. Look at the anticyclonic rotation right here to the south. Looking up the backside of a storm, looking to the east, there's the clear slot from the rear flank downdraft, cyclonic rotation to the north, anticyclonic rotation to the south. Looking to the east, coming on the backside of the mesocyclone area, and we'll put this into time lapse here in just a minute. There's the cyclonic rotation in this area here, left to right across the front, right to left across the rear, just like we talked about in the basic program. Here comes the rear flank downdraft, the clear slot, anticyclonic rotation to the south. Cyclonic to the north, rear flank downdraft in the middle, anticyclonic to the south. Pretty cool seeing this stuff play out in real life. And again, anticyclonic tornado on the south flank of a large supercell. Notice the backward rotation in the cloud base up here. Not the rotation we'd expect to see, but it grabbed that anticyclonic part of the vortex line, tilted it up, accelerated it, stretched it, and produced an anticyclonic tornado. Now, the rear flank downdraft is very important in tornado formation, but not any old rear flank downdraft can produce a tornado. One of the things that we found from the Vortex project, back in the project was in the mid-90s, a lot of the research came out in the early to mid-2000s. The rear flank downdrafts that were associated with significant tornadoes, the air was almost as warm, almost as humid, almost as unstable as the original inflow air that was feeding into the storm. They found that storms that had weak tornadoes or that did not produce tornadoes, there was much cooler air, less unstable air, more stable air that was coming down in the rear flank downdraft. So these significant tornadic cases with the rear flank downdraft almost as unstable as the original inflow air, as the RFD wraps around, it's going to very easily be able to accelerate upward right off the ground, right off the deck, help with that tilting and stretching process that we've talked about. With the colder rear flank downdrafts, though, less vertical accelerations, more outflow pushing out and cutting off these important processes down in the base of the storm. That brings us to keyword number 2 for the evening, vortex. Vortex is keyword number 2. Be sure and copy that down so you can send it in to us at the end of the program. Now, the last ingredient we're going to talk about before we get to our break, so hang in there just a few more minutes, the height of the cloud base. Again, that lifted condensation level, the height of the cloud base seems to be important as well. Some research that was done by Rich Thompson, who is a forecaster at the Storm Prediction Center, looked at thousands of severe storm and tornado cases and found that the cloud base height, among many other things, may play a role. He found that for non-supercell storms, the average cloud base height was about 6,000 feet or about 1,800 meters. Supercells that didn't produce tornadoes had average cloud base heights of about 4,500 feet or about 1,400 meters. Storms that produced weak tornadoes, EF0, EF1, cloud base heights averaged about 4,000 feet or about 1,200 meters. Storms that had significant tornadoes, EF2s or graders, cloud base heights averaged about 3,200 feet or about 1,000 meters. Now, I don't know about y'all, but the times that I've gone storm spotting and done severe weather research and the like, I really couldn't tell a 3,000-foot cloud base from a 4,000-foot cloud base. So there's a little rule of thumb that will help you out with that. If you have at your spotting location weather equipment, you can measure the temperature and dew point at your location. If the difference between the temperature and the dew point is 14 degrees or less, that would correspond to a cloud base of about 1,000 meters, 3,200 feet or less. 4,000 feet corresponds to about an 18-degree difference in the temperature and the dew point. 4,500, about a 20-degree difference. 6,000 feet, about a 27-degree difference between the temperature and the dew point at your location of the air that's actually going to be feeding into the storm. So again, a good little rule of thumb to keep in mind. So here's an example, looking off to the west here at a supercell. Cloud bases were pretty high. We did have a clear slot here. That's where the rear flank downdraft was coming down, wrapping around. But the spotter that was watching this storm noticed very cold outflow as the rear flank downdraft air hit him. Well, before that, the air that was feeding into the storm had a temperature of 92, a dew point of 61, so a 31-degree spread between the temperature and the dew point. Cloud bases were over 6,000 feet, about 2,000 meters, so way too high. A lot of evaporation, a lot of cold outflow rushing out, no tornado from the storm. Now, this storm, we had a lower cloud base. The temperature here was 85 degrees. The dew point was 71. And that gave us cloud bases of just under 1,000 meters here. Looking off to the north, and we can see maybe a lowering off there in the hazy distance. A little bit of a cylinder look to the cloud, to the updraft tower here. So yeah, it looks like it's still a supercell. This is actually the same storm that we were just looking at, but this is about a half an hour later and about 20 miles to the east. The storm got into a much more moist environment. The cloud base is lowered and the storm responded. The spotter moved a little bit north to get away from some of the trees, get a little more of a clearing. Again, low cloud bases. The wall cloud was rapidly, visibly rotating at this time. So the updrafts were accelerating from right off the ground, getting a lot of that tilting and stretching that was taking place in this area. And a few minutes later, the tornado wound up forming. So again, these low cloud bases seem to be important. With a low cloud base, that can also suggest more humidity in the area between the cloud base and the ground, so less chance for rain to evaporate into the RFD and to cool that air. Less of a gust front rushing out, less outflow moving out away at the surface. Again, the more moist the air is, potentially the more buoyant it's going to be, rising up in the rear flank downdraft, again, helping with that acceleration right off the ground, tilting and stretching those vortex lines right down at the ground as well. So here are some key parameters. Now, these are not hard and fast magic numbers. Every storm, every case is going to be a little different, but these are some general rules of thumb to consider for organized thunderstorms or possibly severe storms. And I'll leave this up here for a couple minutes as we go through. You may want to take a picture or do a screen capture of this and keep it for further reference. CAPE, instability, at least 250 joules per kilogram for some sort of updraft. If we start getting into the 4 digits of CAPE here in the Mid-South, we will have enough for significant updrafts. SIN, if we have minus 100, SIN is measured in negative energy, because again, that's what we have to overcome to be able to get the updraft to form. Minus 100 or weaker is probably a cap that can be broken. Much stronger than that, and it's probably going to be difficult for those developing updrafts to punch through and actually develop into full-fledged updrafts. Deep layer shear, again, either the 0 to 6 kilometer or the effective shear. A net change of 25 knots or greater seems to be sufficient for organized storms. 35 knots or greater seems to be significant or sufficient for the mid-level rotation, the mid-level mesocyclones to occur. 0 to 1 kilometer shear, 20 knots or greater for the low-level mesocyclones to form. Storm relative helicity, around 150 is meters squared per second squared is the units that are used, but around 150 or greater seems to be favorable for low-level mesocyclones, low-level rotation. And again, cloud base heights, less than 3,200 feet, less than about 1,000 meters. Now, one point also I do need to stress and kind of emphasize, we talked about the 3-step process for tornado formation: mid-level mesocyclone, low-level mesocyclone, and then the tornado process. Well, that doesn't always happen. Sometimes we'll go straight to the low-level mesocyclone, and then a tornado may spin up from that very quickly. So we don't always see all 3 steps of that process in order, but typically with isolated supercells, the December 23rd, 2015 type storms, that is what we'll see. But again, doesn't always happen that way, especially here in the Mid-South. So hopefully everybody has that captured or a photograph, and we will move on. We are at our break time, so I'm going to stop sharing the screen now, and hopefully there I am. Okay, so Andy will hopefully be joining me here in just a moment here in the room that I'm in, and see if we have any questions from you all so far that we can answer. Okay, well, I guess no questions from the beginning, or Andy got tied up with something else, one or the other. Anyway, we will go ahead. Oh, here it comes. Any questions so far?
We haven't had any big questions at this point. A lot of people just want to know if they can get the information at a later time.
Yes, this program will also be recorded. It's being recorded as we're doing it here live. The same link that you used on YouTube to be able to get to this broadcast, that's the link that you'll use in the future if you want to go back and review this, kind of review some of what we're going to talk about in the future. All right, well, I will go ahead and put the presentation back on. And we will go to break time. So we will see you all back in 10 minutes. All right, everybody, we got less than 1 minute on the break, so you want to be back at your screens if you're not already. All right, we will go ahead and kick off with the second part of the show. And I said you wanted to be back at the screen, and here's why. We've got keyword number 3 now. Keyword number 3, and keyword number 3 is Supercell. Supercell. So again, copy that down. If you want to send it to us to get the participation credit, get your certificate for having been with us here this evening. Now, we talked about a lot of stuff in the first part of the program, a lot of ingredients, a lot of parameters, and a lot of values, and a lot of things that go into organized thunderstorms, supercells, and tornadoes. Well, there are some tools out there for keeping track of those parameters and those ingredients and evaluating them kind of in real time. And they are on the Storm Prediction Center's webpage. Their address up here at the top, spc.noaa.gov. When you get to their main page, click on the Mesoanalysis section, and that will take you to the Mesoanalysis page. From there, you can click on a subsector of a certain part of the country, get a little zoomed in look at what's going on, and then you'll get a screen that looks something like this. A lot of parameters, a lot of things that we can look at. These tabs across the top here. The two that we're going to focus on, though, thermodynamics and wind shear. If we click on the thermodynamics tab, a drop-down menu will appear, and there are all of our capes: the surface-based cape, the ML cape, the mu cape, and then down underneath here, a little further down, the LCL height, the cloud-based height. And these mesoanalysis graphics are updated every hour, done using observations, high-resolution models will go into that as well for the analysis schemes. So it really is up to the hour information. So the mixed layer cape, if we were to click on the mixed layer cape, again, that uses the conditions averaged over about the lowest half mile or so of the atmosphere to calculate how much energy is available in the atmosphere, energy for thunderstorms to form. And this is usually, again, a good estimate of the well-mixed conditions in the afternoon and early evening hours when we've had the heating, we've had the winds, and everything's gotten kind of churned up down here. The cape values on the chart, on the image, are shown by the red lines. You notice that 500 joules per kilogram is where they start with the heavy outlines, then it goes up 1,000 and on up from there. The SIN, or the cap strength, is shown by the blue contours or the blue shading. Minus 25 will be highlighted in a light blue or shaded in a light blue. 100, minus 100 or greater, a little bit darker blue, a little thicker blue shading like we see in here. LCL heights, cloud base heights. The lower the cloud bases, the darker the green. And basically this one medium green contour here would be the 1,000 meter. And then the dark green contours would be heights below 1,000 meters. And again, the lower the cloud base height, the more favorable for low-level rotation and the rear flank downdraft being able to do its thing. Higher cloud bases, on the other hand, might be a better indicator of downburst potential, damaging straight line wind potential from out of any storms that might form. So moving over to the wind shear tab, there's all our different flavors of vertical wind shear as well. Surface to 6 kilometer, the effective layer, that halfway through the depth of the storm, 0 to 1 kilometer, and then the storm relative helicity down here underneath, 0 to 1 kilometer helicity. And the inflow layer helicity is what's shown by the effective storm relative helicity here. And again, this the vertical wind shear, again, helps 0 to 6 or effective will be a good first guess at the deep layer shear, which can help organize the storm, separate the updraft from the downdraft, extend the lifetime of the storm, and induce the mid-level rotation. The wind shear, 0 to 6 kilometer wind shear is actually shown behind here. You notice the contours, and they are labeled in knots. So there's a 70 knot vertical, 0 to 6 kilometer shear, 80 knots, 90 knots over here to the far left, 100 knots up here in Wyoming, it looks like, 60 knots down here in western Arkansas. The effective vertical wind shear, again, shear through half of the expected height of the storms. And again, this is going to be better for particularly short or for particularly tall storms. Now, the effective vertical wind shear, again, up to about goes down to 20 knots. That's the lowest contour that we see. So again, 20 to 25 knots, maybe the threshold for organized storms of some sort. The heavier blue line show we start getting in excess of 35 knots. So again, when the mid-level mesocyclones, the environment would be favorable for the mid-level rotation to occur. The 0 to 1 kilometer vertical wind shear, again, 20 knots is where the dark blue contours start. So again, that threshold for low-level rotation, for the environment to be favorable for low-level rotation to occur, where we have the 0 to 1 kilometer shear, 20 knots or stronger. 0 to 1 kilometer storm relative helicity. The 150, sort of the minimum threshold, is the medium blue contours that we see. 250 or greater, again, suggesting maybe another step up, perhaps, shown in the dark blue. So again, the thick medium to dark blue contours on the storm relative helicity plots. And again, the higher the storm relative helicity, just like the higher the 0 to 1 kilometer shear, the more favorable the environment will be for low-level rotation. Now, we're looking at all these individual ingredients and parameters. Remember, they all have to come together. We have to have the instability to get the updrafts going. Otherwise, it's not going to matter how much vertical wind shear we might have. So all the ingredients have to come together to get these organized severe storms to form. Now, if you want to see what the climatology is like for your particular area, there's another really neat page on the SPC site called the Tornado Environment Browser. You get to that by going to the SPC site, then click on the Research tab, and then click on the Tornado Environment Browser tab. There'll be a national map here in the upper left. Click on the specific area that you're interested in, and it'll load all the climatology, the history, the historical parameters, the normals, and the like for that exact area. In this case, I clicked near Memphis to give us a good sample of the Mid-South. Shows us all the tornadoes that have been reported in the area from 1962 to 2011. Breaks the tornadoes down by time of year and by time of day. Also breaks them down by EF scale as well. Shows us how many violent tornado days we had during that period as well. Over here on the upper right, it shows us the environmental parameters for all tornadoes, that is those that may have occurred with squall lines or with multicell storms, and then the environment for the classic cyclonically rotating supercells over here on the far right. So there's the ML CAPE and what the range of values we typically expect to see. Effective shear, effective helicity, cloud basis. So it kind of shows for your particular area what parameters we might expect to see. And then relative frequency across the nation down here at the bottom right. So again, a lot of really neat information for your particular area from this Tornado Environment Browser. All right, let's talk about radar a little bit now and some basic radar interpretation. If you look at radar, either on our website or on your favorite radar program or radar app that you might have, you'll usually see two flavors, two different types of reflectivity: base reflectivity and composite reflectivity. Base reflectivity is the radar return, the radar display at one particular slice through the atmosphere. And usually this will be the lowest slice, the half-degree slice. Composite reflectivity, the radar will do a three-dimensional scan through the atmosphere about every 4 to 5 minutes or so when we have precipitation or storms in the area. The composite reflectivity will find the strongest return anywhere through the depth of the storm, and that is what gets plotted on composite reflectivity. So composite reflectivity can be handy to look at if you're wanting just a quick look at where maybe the strongest storms in the area might be. But base reflectivity is what you're going to want to look for some of the specific signatures and some of the specific formations that we're going to talk about this evening. We also have two different types of velocity. Now, the velocities that we show, it's called radial velocity. The radar, in our case, is right here, KNQA. Our radar's right very close to Millington Airport. The warm colors that you see, the reds and the yellows and the oranges, indicate motion outbound or away from the radar in this general direction. Outbound, away from the radar. The cool colors, the blues and the greens, indicate motion in towards the radar or in this general direction. And the folks that developed the color scale were pretty sharp, and they set it up so that the brighter the colors represent the higher, the stronger velocities. Now, a couple important things to remember. One is that in some cases, the radar cannot give us the algorithms, the computer programs in the radar cannot give us a reliable velocity estimate. And in those cases, it's going to color it purple. The slang that's called range folding, or the slang term for it is the purple haze. That just means the radar is saying, I can't give you a reliable estimate there. I'm not going to lead you astray, so I'm going to be up front, let you know, I don't know what the velocity is there. So I'm just going to color it purple so you know that. The other important thing to remember about these velocities is they can only measure motion toward or away from the radar. We cannot measure motions across the beam. We can only measure motions along the beam toward or away from the radar. And that's going to become really important when we start looking at trying to figure out what's going on with the velocity signatures that we might see. And speaking of, there are four main types of signatures that we look for in the radial velocity. Again, we're going to use the radar at Millington, KNQA. If we see outbound motions to the right of our particular radar beam, inbound motions to the left of that beam, we can then mentally kind of connect the dots like we're showing with the dotted arrow, the dashed arrows here. This would be a signature suggesting cyclonic rotation, counterclockwise rotation that's going on, what we might expect to see with a supercell, with a mesocyclone. Now, if we see this configuration, again, looking from the radar, looking down here along the beam, if we see inbound motion to the beam's right, outbound motion to the beam's left, again, think you're here at the radar, looking down in this direction, outbound to the left, inbound to the right of the beam. Again, mentally connecting the dots using these dashed arrows like we're showing, this would be a signature suggesting anticyclonic rotation, like we might see within a left-moving supercell from a split, for example. If we have this configuration, outbounds further away from the radar, inbounds closer to the radar, this is an indication of divergence. Things are spreading out, spreading apart in this location. This is what we might expect to see with a downburst that hits the ground and starts to spread out. We also can sometimes see divergence up at the top of the storm where the updraft is slowing down and the anvil is spreading out up at the top of the storm. And then finally, if we have outbounds closer to the radar, inbounds further away, this is a signature suggesting convergence, things coming together in this area. This is what we might see underneath a strong updraft that might be close to the radar. We can actually sometimes see the inflow going into a storm. Or this is what we might see in the mid-levels of the storm where a downdraft is getting started, maybe a downburst is going to try to form. Now, it's very important, like I mentioned earlier, that we know where we are with respect to the radar. Because if you just look at the colors, we have green to the left, red to the right, green to the left, red to the right, green to the left, red to the right. But it's the position of that signature with respect to the radar that physically tells us what's going on there. And we'll go through a lot of examples coming up here, and it'll, with some real life examples, hopefully be a little easier to visualize. Two different types of velocity that we have. Base velocity is ground relative. This is how the particles are moving with respect to the ground. Base velocity is going to be best for estimating straight-lined wind speeds, like with the gust front, the big outflows pushing out ahead of the lines of storms, for example. And again, if we have a storm that's close enough to the radar, very close to the radar, we can sometimes even estimate the inflow going into the storm as well. The other type of velocity is storm relative velocity. And again, both of these velocities will be on our radar site and on your favorite radar app and radar provider as well. With storm relative velocity, we've subtracted out the storm motion. This is kind of what the storm is feeling as the storm is moving along. Storm relative velocity is best for identifying rotation signatures. For example, this area down here, notice in the base velocity, we had some really strong inbounds here. That bright purple would be very strong inbounds, very strong negative velocities here. Weaker inbounds over here, maybe 10 to 20 knot inbounds here. So, okay, there's maybe a little shear there, but it doesn't really jump out like it does in the storm relative velocity, where we have very strong outbound right next to very strong inbound. Again, the radar is up here. So the outbounds in this direction, the inbounds in this direction. So that would be the cyclonic rotation signature here. Now, you need to be a little careful when you're looking at these velocity products because they kind of look the same. These velocity images kind of look the same. You'll see some warm colors. You'll see some cool colors. Maybe you'll see some purples thrown in. They'll look kind of similar sometimes. Make sure that you're looking at the image title to make sure you're looking at the right velocity for the situation. Here's an example why we need to do that. Here's storm relative velocity. There's a line of thunderstorms shown by this orange dash line that's moving from west to east, approaching us here in the Memphis area. Right ahead, there's some strong inflow feeding into this line of thunderstorms, but you look behind the leading edge, behind the gust front area, we have some inbounds here, so some motions from west to east in this area. But you look at you compare the colors here to the color scale over here to the far left, and some dark to medium greens, so maybe 20 to 30 knots, maybe 25 to 35 mile an hour. It doesn't look like it's going to be that big of a deal when it comes in. We're looking at the wrong velocity here. Remember, for straight line winds, we need to be looking at the base velocity. There's what the base velocity was at this point. Well, it looks a little different. Some very bright greens getting into some of the light blues here near Earl and Parkin. So maybe 50 to 55 knots, 55 to 65 mile an hour velocities in this area. So definitely a much different picture from what the storm relative showed. So again, make sure you're using the right velocity image for what it is you're trying to see. Base velocity for the straight line winds, storm relative velocity for the rotation, convergence, divergence type signatures. That brings us to keyword number 4 for the evening. Keyword number 4 is velocity. Velocity. Get that written down if you're going to want to get the certificate of attendance from us at the end of the program. We'll give you the instructions again, what to do with these keywords. So what are some of the radar signatures that can suggest strong or severe thunderstorms? High reflectivity values. Now, reflectivity is measured in a unit called dBz. That's not real important to you, but there will usually, again, be a color scale showing what color represents what dBz value. And if we start seeing dBzs in the upper 50s to lower 60s, very heavy rain, maybe some hail. If we start seeing upper 60s to around 70 dBz, probably hail there. If not, then it's extremely heavy rainfall in those cases. We'll also look for a tight reflectivity gradient, usually on the south or southeast side of the storm. What do we mean by that? Well, a very fast transition from no or very light return to very strong return, again, over just a very short distance here. This suggests that the storm is well organized. We have a strong updraft area and maybe a strong downdraft area as well. Now, remember, radar detects precipitation and other targets. So if we have a strong updraft area, we usually would not expect to see a lot of precipitation in that area. And that's what we see here. Again, this kind of echo-free, this return-free area, highlighted with the yellow, is where the main updraft area of this storm would be. A spotter that was out in this area looking off to the west of this storm, that's where you're going to see the rain-free base and the updraft towers building up, again, in this yellow highlighted area here. Here's the signature of a microburst. Here's the reflectivity. The radar is here, so we're looking off to the southeast at this storm, or east-southeast. High reflectivity, so very heavy rain, maybe a little bit of hail taking place in that area. But we go to the velocity, and here's what we have. Outbounds further away from the radar, inbounds in closer to the radar. So there's one of those divergent signatures spreading out as the downburst of the microburst hits the ground and starts to spread out away from where it hit the ground. Here's the radar loop showing the bow echo, again coming from in the western portion of the image here. Again, bowed out looks, so maybe some very strong winds ramming into the backside. Again, that strong rear inflow coming in, mixing down to the ground, very strong straight line winds out here at the leading edge of the bow. Maybe some short-lived tornadoes up here on the north end of the bow. We can also actually sometimes see the outflow boundaries, the gust fronts on these with the radar as well. This thin, fine line that you see, a very light return here, that's not precipitation, that's not rain. That may be some dust or some bugs or some insects. Also, we can sometimes get a little return just from the temperature, the density gradient from the very warm air out here to the rain-cooled air back in here from the outflow winds that are pushing out. Sometimes, now the storm does have to be in fairly close to the radar for us to be able to actually see the gust front, see the outflow like we can here. But when we do see it, it can help us identify where the strong outflow winds might be occurring. And also we can see maybe if the outflow is starting to try to outrun the storms, or if the outflow and the storm motion are in good balance like we talked about earlier. So when it comes to velocity and rotation, you'll hear us use some terminology, or may see in blogs or whatnot, various terms to describe the strength of the rotation that's being observed. One term that we'll hear is rotational velocity, and this is basically just the average speed of the rotation. We take the maximum outbound, the maximum inbound, divide it by 2, and that gives us the rotational velocity, again, the average speed of rotation in that circulation. Now, there is no single magic value that tells us that this storm is a good tornado candidate or this storm is not. It depends on how far the storm is away from the radar. The radar can see these signatures a little sharper, a little clearer, and closer to the radar. Things are a little more smeared out the further away from the radar you get. So the key values are dependent on how close or how far away the rotation is from the radar itself. You also may see delta V which is the velocity difference. Again, just what is the difference between the maximum outbound and the maximum inbound? This will also be dependent on how far the storm is, the rotation is away from the radar. Again, the closer in we are, the easier, the sharper the detail that we're going to be able to see. You may also hear the terms gate-to-gate and broad. Gate-to-gate rotation means that the maximum outbound and the maximum inbound are right next to each other. They're butted right up against each other like we see here. Broad rotation is when the maximum outbound and the maximum inbound are some distance apart from each other, maybe several pixels in here of distance between the maximum inbound and the maximum outbound. So that would be broad rotation. This would be gate-to-gate rotation. So what are, again, some of these other rotation signatures that we look for, things that might suggest the storm is rotating, that the storm is a supercell? Well, in the reflectivity image, one thing that we look for is the hook echo, like we show here. Let me back up here. The hook echo, like we show here. Again, the hook echo does not necessarily on its own suggest a tornado, although there is one other feature in here we're going to talk about that suggests a tornado may be going on here. The hook echo, though, is an indicator of the mesocyclone, the supercell, the larger scale rotation that's taking place. And again, the hook echo is this kind of fish hook or figure 6 type shape that we see in the reflectivity right in here. Now going to the velocity, storm relative velocity. The radar is to the northwest, so we're looking down to the southeast at the storm, and we do see a couple of scales of rotation that are taking place here. We have an area of maximum outbounds right in here, the bright pinks that we see, an area of maximum inbounds here, the medium blues that we see. This is the mesocyclone that we're seeing, the larger scale rotation, the updrafts tower scale rotation, again, maybe 3-4 miles or so across on the average. So that's the mesocyclone scale that we're seeing there. But if we look closely here, inside that mesocyclone rotation, we have very strong outbounds right there, the bright yellows, very strong inbounds, that little dark purple that we see right there. That is called the tornado cyclone. So that would be the wall cloud scale rotation that's taking place. So that would be more suggestive of possibly a tornado occurring with this storm. And in fact, this is what was taking place at about that time as these radar images, a large, violent tornado. Actually, 7 years ago tomorrow, this was one of the April 27th, 2011 significant outbreak in northern Alabama. Now, we also have algorithms that are part of our radar system. These are computer programs that assist us in analyzing the storms. Some of your radar providers and apps will have some of this algorithm output as well. Again, these are computer programs that can estimate various things about the storm. Hail size estimation, how strong is the rotation? Is it a mesocyclone? Is it one of those tornado cyclones? Estimating how much rainfall has fallen from out of the storm in a certain period of time. And these are based on three-dimensional storm structure, studying a lot of storms and looking at the three-dimensional structure and just kind of doing some correlations on what we would see about how much reflectivity in the upper part of the storm, how strong is the rotational velocity based on how far away the storm is, things of that sort. These algorithms are getting better and better. Again, they're valuable in helping us analyze the storms, but they are only tools. They are not the gospel. Just because a computer algorithm says there's a tornado taking place or that there's golf ball size hail taking place, that doesn't necessarily mean for sure that's what's happening at the ground. That's the job of you all, the storm spotters, to confirm what the electronic tools suggest might be happening or not happening around a storm. Now, a few years ago, we got an upgrade to the radar called dual polarization or dual pol. And this has opened up a whole nother set of data as far as being able to analyze what the radar is detecting, what the radar is sensing. Now, the old radar, the regular radar, basically detected precipitation particles in the horizontal. The dual polarization radar, the dual pole, detects in the horizontal and it detects in the vertical. So we get a lot better idea of the shape and the size of the targets that the radar is detecting for us. There are three main types of dual pole products that we look at. One is called differential reflectivity, which tells us how much return are we getting in the horizontal versus how much are we getting in the vertical. So the shape of what it is that the radar is detecting. The second one is called correlation coefficient. This is a measure of how similar or how different are all the targets in each of those pixels, each of those individual pixels that's making up the display that we're looking at, the image that we're seeing. And then the third one, it's a really exotic thing called differential phase. We're not going to get into that one this evening, but basically that helps us tell how much liquid is in each of those pixels. That can be useful for estimating where heavy rainfall is taking place. But differential reflectivity, correlation coefficient, those are a couple that we're going to talk about because those are most directly applicable. We can most use those when we're talking about potentially severe storms. So a differential reflectivity, if we have a raindrop, like we show here on the left, raindrops as they fall do not have the teardrop shape like you might see in some paintings or cartoons or the like. Raindrops, when they fall, actually get squished into kind of a flat shape like this, kind of like a hamburger bun, the way that they're shaped. So we will get a lot more return in the vertical than we will in the, or a lot more return in the horizontal, excuse me, a lot more return in the horizontal than we will in the vertical. And so the differential reflectivity on the image, on the plot, will show up as much greater than 0, +3, +4, +5, somewhere in that range. If we have an ice crystals tend to be kind of tall and skinny, like we show here. So we'll get a lot more return in the vertical than we get in the horizontal. And the ice crystals will show up as less than 0 on the ZDR, -1, -2, somewhere in that range. But if we have something that's just about round, we're going to get just about equal return from the horizontal and the vertical. So the differential reflectivity, or ZDR as it's called, will be right around 0. And again, that's a big round thing, and that's what we often see with hailstones. Excuse me. So looking at a couple radar images, we have reflectivity here on the right, or on the left, excuse me, differential reflectivity on the right. In the regular reflectivity, very high returns. The purple's there, upper 60s, lower 70s, dBz values, so very high returns there. Right in that same location, we have ZDR values that are very close to 0, those medium to darker blues in there. So a lot of something, and whatever it is just about round. So probably hail in this location. Now look out around here in the right on the edge of the oval that we have highlighted. Some pretty high reflectivity still. The oranges, the reds, so 50, 55 dBz. But notice that the differential reflectivity, the ZDR values, pretty high as well, +3, +4. So again, probably those big old flat squished hamburger bun shaped raindrops in that location. Okay, correlation coefficient. Again, the radar, it can basically measure how similar or how different are the targets in the sample volumes, those individual pixels that make up the image. Correlation coefficient ranges between 0 and 1. So if we have a pixel that has all raindrops and they're all pretty close to the same size, they're going to be pretty close to the same shape, of course. So that's going to give us a very high correlation coefficient, 0.98, 0.99, very close to 1. But if we have a sample volume, a pixel, that has maybe some raindrops, maybe some hailstones, maybe some snowflakes, well, things are going to be Much different shape, much different sizes in here. So that's going to produce a lower correlation coefficient, maybe 0.92, 0.90, 0.94, somewhere in that range. The correlation color coefficient, now fortunately, most everybody we hear on our workstations and most all the radar providers, radar app developers, have pretty much used the same color scale for correlation coefficient. So this should be pretty valid for what you look at. Again, 0.96 to 1, the dark reds, the purples, the pinks, that suggests things are all pretty much the same size and the same shape. All raindrops, all snowflakes, whatever's being detected. 0.85 to 0.96, the greens, the yellows, the brighter reds, more mixed precipitation, rain and hail, rain and snow, for example. If we start getting down into the blues, though, 0.6, 0.7, that probably suggests non-meteorological targets, insects, dust, birds, and maybe some other things that we'll talk about here in just a minute. Right now, in fact, tornado debris can also be detected using the correlation coefficient. So here in the upper left is the reflectivity. This is from the Tupelo tornado from 2014. There's the hook echo right there, right about over the L in Lee for Lee County. The radar, this was the Columbus Air Force Base radar. So the radar is down here to the southeast, looking to the northwest. There's our strong outbounds. There's our strong inbounds. So the cyclonic rotation, the mesocyclone right in this area here. And hard to see because it's right about, again, right behind the L in Lee. Very strong outbounds, very strong inbounds, gate to gate. So that would be the tornado cyclone signature. Also right about in that area, the correlation coefficient, the dark blue here, very low correlation coefficient values. Also where we find the velocity signature, also where we find the hook echo. But this is, again, the indication of the tornado debris that was being picked up, lofted high enough for the radar to be able to see it. So again, you may want to take a picture or a screen capture of this, some of our key radar parameter guidelines. Again, none of these are hard and fast magic numbers, just like we talked about before, but just some general guidelines. Again, each storm is going to be different. Reflectivity, upper 50s into the 60s, maybe to the lower 70s, very heavy rain, possibly hail. Reflectivity structure, if we have the sharp reflectivity gradient, that might suggest an organized storm, strong updrafts and strong downdrafts. Bow echoes can suggest, again, the straight line wind potential. If we see any curvature on the south side of the storm, or again, the full-blown hook echo, that may suggest rotation, a mesocyclone taking place with the storm. The velocity signatures, again, strong base velocity, might suggest an area of straight line wind at the leading edge of a line of thunderstorms. A strong and tight signature will suggest rotation. And again, no magic values, but roughly speaking, the stronger and tighter the signature, the higher the possibility of a tornado from out of the storm. ZDR values, +2, +3 or higher, probably those big raindrops. ZDR values near 0, suggesting round objects. Again, if we have high reflectivity in that area, maybe large hail taking place. Correlation coefficient, again, greater than about 0.96, probably a single type of precipitation. 0.85 to 0.96, some sort of mixed precipitation. Lower than 0.85, some sort of non-meteorological targets, probably. That brings us to keyword number 5, correlation. Correlation is keyword number 5. Make sure, again, jot that down to turn in when we give you the instructions at the end of the program. Okay, coming down the home stretch now, we're going to kind of put it all together into a case study and go through pretty much everything that we've talked about this evening. We're going to use some of the SPC mesoanalysis graphics, excuse me, and evaluate some of the key parameters, try to anticipate what the environment might favor on this particular day. Again, determine their impact on the storm environment, estimating again what type of storm we might expect, what type of evolution and behavior we might expect to see. We'll then take a look at some radar features, try to identify and interpret some important things that we might be looking for on radar, estimate the potential impacts of the storms, then confirm with some spotter photos as well. So here's the surface weather map at 3 p.m. on this particular afternoon. And we're not going to get into all the gory details here, but the sticks here indicate the direction from which the wind is coming. So wind's generally from the south, coming up into Mississippi and West Tennessee and the Mid-South, 10 to 20 miles an hour basically coming up into this area. Temperatures largely in the 70s, upper 70s down here in central Mississippi coming up into the area. Dew points in the mid to upper 60s. The highest dew points, so the greatest surface moisture, right to here coming up through this axis in western Mississippi into far west Tennessee. A little bit to the west, you notice the winds are more out of the southwest or the west here in Arkansas, Oklahoma, far Louisiana area. So this is a trough, a line of low pressure, and these areas can be favorite areas for lift to occur, small scale lift to occur where thunderstorms might be expected or favored to form. So looking at some SPC mesoanalysis graphics, looking at the mixed layer cape, looking at the red contours, there's 500, there's 1,000, there's 1,500, starting to work up into some of the delta areas in western and northwestern Mississippi. Again, 1,000 across a lot of northwest Mississippi, eastern Arkansas, into southwest Tennessee. The SIN, the cap, the lid is pretty much all over northeast Mississippi and into Alabama. So no real major lid, no real anything that's going to be blocking, no stable air that's going to be blocking the updrafts from trying to form here in the Mid-South, and especially, again, southwest Tennessee, northwest Mississippi, east central Arkansas. Looking at the effective shear, the deep layer shear, 65 to 70 knots, where we had those maximum instability values. So thinking back to your key parameters diagram or your list from earlier, again, we said 35 was kind of the threshold for supercells, mid-level mesocyclone formation. So we certainly are well above that threshold. Looking at the 0 to 1 kilometer shear, again, focusing on where we had the strongest instability. 0 to 1 kilometer shear, let's see, there's 20, 25, 30 knots, 35 knots, 40 knots, northwest to north central Mississippi, again, east central Arkansas and southwest Tennessee. So certainly sufficient low-level vertical wind shear for low-level mesocyclone formation. 0 to 1 kilometer storm relative helicity. Again, the 150 here, 200, 250, the darker blue contours. So a little less favorable, not as favorable, we should say, kind of right along the delta in west central to northwest Mississippi, but becoming more favorable as we move north and northeast from there. Certainly favorable overall for low-level rotation. And the LCL heights, the cloud base heights, there's 1,000, there's 750 meters, there's 500 meters. So cloud base heights below that 1,000 meter limit. So again, the environment probably would be favorable for not a lot of evaporation, cooling, and outrush of cold air from any storms that were to form. Well, storms did form in northwest Mississippi. This is what the radar looked like at 2:58 p.m. Again, the radar, we're using the Millington radar, our radar, and it's up here to the northeast. So we're looking down kind of to the south-southwest at these storms. And there's a storm there south of Clarksdale, west of Matson, just east of Alligator. Taking a look at the shape of that reflectivity, I'll give you a minute just to look at it and see if you can pick out any features there. And there's not a whole lot that we can see from the reflectivity. So if you're not seeing much, don't feel too bad. There's not a whole lot here. We do have some pretty high reflectivity values, upper 50s, maybe pushing 60 dBz up in here. Maybe a little bit of curvature and gradient here on the south side of the storm. So maybe a sign from the reflectivity. Maybe a sign that there's some rotation in here, but we probably ought to look at the storm relative velocity and try to tell for sure. So we go to the storm relative velocity and wow, yes, there is rotation there. There's the maximum outbounds, somewhere probably in the 40s, looking at the color scale here, upper 30s to 40s. There's the maximum inbounds, probably upper 50s to the 60s, again, looking at the color scale. It's pretty much gate to gate. They're pretty much right next to each other there. So yes, indeed, we have a cyclonic rotation that's going on in this area. And if we do the calculations on it, the rotational velocity would be about 46 knots there. And using some of our tables that we have, looking at the distance there and the rotational velocity, this will be classified as a strong mesocyclone. So about 20 minutes later, the storm has moved on up. It's east of Clarksdale now, just west of Marks. And looking at the reflectivity, again, we have still the pretty high reflectivity values, upper 50s anyway. Any other features evident in the reflectivity? I'll give you just a moment to look at it here. See if you can see anything. Well, again, not a lot of really obvious signatures that jump out at us. Still, again, some curvature on the south side here, so suggesting maybe some storm rotation still taking place. We go to the storm relative velocity, and there is our signature now. Now, one thing you'll notice is the circulation looks like it's broadened out some. There is the maximum outbound. Over here is the maximum inbound. So there's quite a distance now, a little bit of distance between the two. They're not gate to gate. They're not butted up right next to each other like they were about 20 minutes ago. But we do still have certainly a mesocyclone signature taking place here, mesocyclone scale rotation that's taking place. And if we do the calculations, we get a gate-to-gate rotational velocity in there of about 38 knots. So that becomes a moderate mesocyclone would be the classification. So you might think to yourself, wow, the rotational velocity is decreasing. The rotation signature is broadened out some. Maybe the storm's starting to lose its intensity. Maybe it's starting to kind of fall apart on us, and maybe the threat's diminishing. Well, let's take a look at the correlation coefficient and see what it shows us. Right in that area where we have the rotational velocity, the rotational signature, we have a little correlation coefficient minimum that's showing up. So that might suggest tornado debris that's been lofted. Now, is that still going on, or is that tornado debris that's just been lofted up from an earlier tornado and when we had that tighter circulation? Well, how are we going to figure that out? Well, the best thing we can do is turn to you guys, turn to storm spotters, and see what the visual is. And about 5 minutes before this radar image was taken, that was what the storm spotters were seeing. So yes, something significant certainly going on still. This was southeast of Clarksdale, obviously a large tornado taking place. Notice the clear slot also, again, rear flank downdraft, wrapping around, providing those vortex lines that are getting tilted and stretched by the updraft acceleration, helping with that tornado. So we jump about 45 minutes or so later, an hour or so later, and the storm has moved up into Marshall County, and hopefully you don't have any difficulty seeing the hook echo now. In fact, it's not only a hook echo, it's almost a donut that is formed here. Probably some widely spaced raindrops, maybe a few hailstones in this area. So high radar return, but spotters were able to still get a visual on what was going on in this area. The storm is now southeast of the radar. Radar is up in this general area, so we're looking down to the southeast at it. And there's what we're seeing on the velocity. Again, we have the large scale circulation, the mesocyclone scale circulation in here. And if we look inside there, strong outbound, strong inbound, right next to each other, the tornado cyclone circulation right in there. If we do the rotational velocity calculation, excuse me, on this gate-to-gate signature, 64 knots, it's basically off the scale at this point. As you probably would guess, there is also a correlation coefficient dropout minimum in that area, so tornado debris signature, and this is what was going on at about this time. So you probably have figured out now this was the December 23rd, 2015 tornado event down in northern Mississippi. Long track, strong to violent tornadoes. The first tornado was an EF3. The second tornado, an EF4, the one that moved up through Holly Springs, northern Benton, Tippah counties, and actually dissipated up near Selmer. Earlier in the day, we did have supercells in northeast Arkansas, did not produce tornadoes, but did produce up to tennis ball size hail. So significant damaging hail up in northeastern Arkansas as well. So kind of wrapping things up for the evening. As violent and as destructive as severe thunderstorms and tornadoes can be, we really need a pretty delicate balance of environmental ingredients to get those severe storms, in particular the outbreaks, the widespread severe storms like we see. It's much easier for the process to fail than it is for the process to complete. Radar is an important electronic tool for detecting and observing these severe storms. It does require, though, an understanding of the radar and, again, how the radial velocities work. Again, knowing where the storm is with respect to the radar, knowing some of the processes that we'd want to be looking for from the storm. So we're expecting a microburst or a mesocyclone or a big gust front from out of the storms. But really, again, these are all just tools. The forecasting, the radar, it's all just tools, just like the information we get from you as storm spotters. When we can combine all that together, knowledgeable spotters, skilled forecasters, proactive emergency management, aggressive and knowledgeable media partners, that is when we have the best possible warning system. And always, again, safety must be first. No matter how much you know, how experienced you are as a storm spotter, safety has to always be the #1 priority. And this brings us to our final keyword of the evening, keyword number 6, and that word is debris. Debris is keyword number 6. So what do? Well, if you want to receive credit and get it'll be an electronic version probably of a certificate of completion from us for advanced spotter training, email the following info to sr-meg.wx@noaa.gov. Email us those 6 keywords that we displayed through the program. Give us your name, your physical address, where you are physically located, city, state, zip code. Kind of like we did with our form on the basic spotter program, where you are with respect to the nearest city that you live in, 10 miles west of Dyersburg, for example. And the best way to contact you, especially if it has changed if any of this has changed since you filled out your basic spotter training paperwork. So again, the keywords, your name, your address, your physical location, best way to contact you. And if you're on social media, let us know your Twitter handle as well. That way we can kind of know to look out for you and know that you're one that's knowledgeable and will give good quality reports and information. So some other helpful links that you might want to look into if you want to learn more. The SPC analysis, mesoanalysis pages, that's the direct link there. Again, you can get to them, though, just from the SPC main page as well. If you'd like to learn a little bit more about the dual polarization radar, there's an online training course that our training branch developed, and the web address is there. For real-time weather information, observations, and the like, the National Center for Atmospheric Research has a good website to use as well. If you'd like to learn more about just general weather information, Weather Service has an online program called Jetstream, which has, again, good general weather information. If you want to go back and look at a severe weather event in the past, Storm Prediction Center also has an archive of past severe weather events where they show the storm reports they received, the watches, the warnings, the convective outlooks, and some of the meteorological conditions that came together, the ingredients that came together to produce those events. So if you're a weather history buff, that can be a good source to look at as well. So again, if you have any questions, you can tweet to us, Facebook us, not just now, but if you come up with questions later on in the program, then you certainly are welcome to tweet us or contact us as well. Again, the Twitter information handle, our Twitter page, and our Facebook page, Facebook information as well. If you knew and understood pretty much everything that we talked about in this program this evening, you are definitely to be congratulated. If you got some of it, then certainly pat yourself on the back for that. If a lot of it didn't make a whole lot of sense to you, that's okay too. Again, there's going to be a permanent version of this at that same link that you went to see this live broadcast. You can go back and rewatch as much as you want. And if nothing else, you hopefully got an appreciation for how complex tornadoes and severe thunderstorms can be, and the challenges that we face when it comes to trying to forecast these potentially dangerous events. So that is what we have for you this evening. Andy, I will turn it back over to you if you're there, and if we have any questions, and I'll turn it back over to you for any closing comments. Again, thank you to the Memphis chapter of the American Meteorological Society and National Weather Association for hosting us this evening, and thank all of you all for tuning in and joining us this evening. I will stop.
Well, thank you, Gary. That was an excellent presentation. I hope everyone learned a lot. Congratulations to all of our new spotters, advanced storm spotters. We're lucky to have you guys. Obviously, the Mid-South is kind of a difficult place to spot. Northeast Arkansas, a little bit flatter across the Mississippi Delta. Obviously, trees and things like that are difficult for us, but we get plenty of storm structure, as Gary covered in the presentation. Did an excellent job. We did have, I think, one question, Gary, came from Cameron Adams. Pretty much he asked, and it was covered, I think, in there, but a good rule of thumb on how to remember which direction the radar is coming from, reds and greens.
Yeah, that's a good question, and part of it is just knowing your local geography and knowing where the radar is with respect to where you're going to do your spotting. For example, if you live in Madison County, well, the radar is going to be looking off to the east or northeast at you probably. If you live in Marshall County, the radar is going to be looking to the southeast. But also, if you look very closely at the radar image, you'll see that the pixels almost make like very thin pie slices as they go out away from the radar. That can help tip you off as well. But again, the easiest way is just knowing your geography, knowing where you are, knowing where Millington is, and then that'll help you out with what direction the radar is looking. Great question. Thank you. Excellent, Gary. That was great. We want to let you guys know, obviously, the AMS and NWA chapter, we're always looking for weather enthusiasts. We bring together a wide variety of people in the weather enterprise. We have FedEx, we have education, lecturers, we have people that are just hobbyists, ham radio operators. So we're always looking for people to join our group. We have meetings every couple months. We have officers and stuff. We also do scholarships. So any future meteorologists in the making, they're looking to get some help financially, we offer scholarships and things like that. I'll just briefly share with you guys our page here. And so this is what it looks like. It's just amsmemphis.org. And obviously here on the front page is some information about what we do and when our meetings are. There's a link here for the chapter scholarship now available. So if you want to apply for that, it'd be great. And we also have all kinds of stuff on here. Our meetings, previous ones with presentations that people have provided, some stuff on Go 16, presentations from Tom Salem, our suit. So there's a lot of information on here, and we'd love to have you guys
Once again, thank you for attending our spotter talk tonight. We're very happy to have you guys as advanced spotters. Please remember to send in the information to the email along with all the keywords as how you'll get credit for the information. Once again, this will be recorded, so you'll be able to get the information after we end this broadcast. I think it'll take a couple hours. It'll show up and you'll be able to screen capture or view some of the information, as there's quite a bit that we gave you guys tonight. So thanks again. Thanks to Gary Woodall, who's trained nearly 5,000 spotters or more. Thanks to him for providing us with an excellent presentation on advanced storm spotting techniques. We hope you guys learned a lot, and look for more spotter talks in the near future. And be sure to leave questions, comments, anything on our top chat there. So thank you guys for joining us, and have a great evening.